So let's look at one last example. So in this example, we have x of t equal to exponential 2t, right? So this is a exponentially increasing function, but it's non-zero. It's multiplied by u of minus t, so it's non-zero only for t that is negative, right? So your function x will actually look something like this. That is 0 for the positive axis. Okay. Now, what is h of t, right? H of t here is something like this. Okay. So h of t is the unit step function shifted to 3. So it looks something like this. All right. Now you want to take the time reversed version of h and slide it over this x. Okay. Now this is a little bit tricky, right? Because the rising point is not at the origin, right? So you have to be careful with this. When you perform a time reverse, this edge now appears at -3. Okay. So then when you shift to time t, the edge will occur at t -3, right? So suppose you have, okay, so suppose this is h of t minus tau, right? If you take the time reversed version and shift it by t, then the edge actually occurs at the time instant t -3. Okay, so you have to be careful with identifying the position of this time shift. Right. So suppose we first look at the case where t -3 is less than 0, right? So that this rise is in the this edge is in the negative axis. Okay. Then x of tau, h of t minus tau, is equal to e to the 2 tau for tau less than t -3 and 0 otherwise. Okay. So in this case, y of t is integral up to t -3 e to the 2 tau d tau, which gives me 1/2 e to the 2 times t -3. Okay. Now, for t -3 that is greater than 0, right? When t -3 is at in the positive axis, then the entire input signal will be included in h, and therefore you have x tau h of t minus tau equal to e to the 2 tau for any tau less than 0 and 0 otherwise. So if you take the integral over this, right, you are taking the integral from -infinity up to 0 e to the 2 tau d tau, and this is just 1/2. Okay. So for t -3 that is greater than 0, right? No matter where this position t -3 is, we're always integrating over the entire x of tau. So you get a constant there. Okay. So if you want to plot this out, right, eventually you get a y of t, okay, y of t that increases exponentially up to time t -3 equal to 0, or let's say t equal to 3, and after which it becomes 1/2. So you get something like this, that is 1/2 for t greater than 3, and then monotonically increasing up to that, exponentially increasing up to time 3 for t minus 3 less than 0. Okay. All right. So do we have any questions? Basically what we're doing in these few examples is just to compute the continuous time convolution. Okay. 所以赖彦凯在吗？
哎，喂，老师。
所以在这个课之前，你们有算过这个 convolution 吗？
常微分方程的时候有算过。
在微分方程的时候有嘛？对不对？
对。
OK。所以这应该不是第一次大家接触这个 convolution， 是吗？
应该是。
OK。好，谢谢。All right. So if this is not the first time that you have encountered convolution, we can maybe go faster here. Okay, let me switch to the next set of slides. Okay. So up to this point, we have learned that, for linear time-invariant systems, we can characterize the input and output relation using either the convolutional sum or the convolutional integral, right? So basically, the output in discrete time LTI systems is equal to the input convolved with the impulse response. Okay, and similarly in continuous time, y of t is equal to the input, the convolution between the input and the impulse response in continuous time. Okay, so from these relations, we can see that we can compute the output for any input as long as we have knowledge of the impulse response. So as mentioned earlier, this implies that the characteristics of an LTI system is completely determined by this impulse response, right? Either h of n or h of t. Okay. But notice that this is not true in general, right? Especially when you are looking at nonlinear systems. Okay, so this is true only for LTI systems. Okay, so in fact, suppose that we know we obtain the impulse response h of n that is equal to q for n that is equal to 0 and 1 and 0 otherwise. Okay, so h of n is the output when you insert a delta function at time 0. Okay. So for an LTI system, right, if your system is linear time invariant, specifying the impulse response characterizes completely the input and output relation. Okay. So in fact, just by plugging this into this convolutional sum here, you will find that the output at time n can be written as q times the input at time n plus q times the output, the input at time 1. The input at time n minus 1. Sorry. Okay. So for LTI systems, knowing the impulse response, the response to an impulse at time 0, you will be able to completely characterize the input-output relation. Okay. But this is not true for nonlinear systems, right? So suppose that your system is nonlinear. Okay. Then your input-output relation may not be unique. It can be several different things, right? So for example, you can have yn that is equal to q xn plus xn minus 1 squared. Okay. So for this system here, if you take x of n equal to delta of n, you will again get an output response that is equal to q at time 0 and at time 1. Okay, so if you take x as delta of n, then you have q of delta n plus delta of n minus 1 squared, and the output will again be q at time 0 and 1. Okay. Now, if you take yn equal to q max of xn and xn minus 1, okay, then you can see that the output of a impulse, the output of the response to an impulse at time 0 is again equal to q for time 0 and 1 and 0 otherwise. Okay, so this shows that, just giving you the response to an impulse at time 0 for a nonlinear system does not tell you, or it does not characterize completely, the input and output relation for this system. Okay? So being able to use the impulse response to characterize fully the system is a very special characteristic of linear time invariant systems. Okay. So oh, sorry, let me switch this around. So next we want to talk about a few properties about this convolution, right? This convolution operation. Okay. So in particular, we want to show that we're going to show that this convolution satisfies the commutative property, the distributive property, and also the associative property. Okay, and there are also system implications because of this. Right. So starting from the commutative property, right? This says that the convolution of the sequence xn and hn is equal to the convolution of hn and xn. Okay, and similarly for the continuous time case as well, right? So you can switch the positions of this convolution and you will get the same result. So this is rather straightforward to show, right? So you can just start out from this xn hn, right? Which is xk hn minus k summing k from minus infinity to infinity. Okay. Now we can do a simple change of variable where we set r equal to n minus k. Right. So if you do that, then you have now a summation for r from minus infinity to infinity, x of n minus r and h of r. Right? And this is exactly in the form of the convolution between h and x. Okay? So just by a change of variable, you show that this convolution is a commutative operation. Okay, so you can do this similarly for continuous time, right, to show that xt convolved with ht is equal to ht convolved with xt. Okay. Now, what does this mean? Right. So previously, when we suppose we look at revisit this example 2.4, right? Previously, when we showed how to compute the convolution between x and h, we showed that we should first take the time reversed version of h, right, and slide it through x, right? But what this commutative property tells us is that we can actually do this the other way around, right? So we can also treat h as the signal, right? And then take the time reversed version of x instead and slide it over h. So we can take the time reversed version of x and then slide it through the function h. Okay, so both of these approaches give you the same result. Okay. Now, if you look at example 2.7 again, right, this has the same implication, right? So previously, when we wanted to compute the convolution between x and h, we started out by taking the time reversed version of h, and then sliding this over x. Okay, but the commutative property tells us that we can also do this the other way around, right? We can actually take the time reversed version of x and slide it over this function h. Okay. Now this is convenient because we can choose one way that makes our computation more intuitive. Okay. Now usually it may be easier to slide the function that is simpler looking, right? So for example, if you slide this window, right, or this constant value over some window over some function h that is time varying, then you're basically just taking the summation or integral over a certain window of h, okay, which is much more intuitive to compute, right? So whichever is more convenient, you can choose to do that. Right. So other than the commutative property, right, we have this distributive property, which tells us that if you take the convolution between xn and the sum of h1 and h2, then this is equal to the convolution between x and h1 plus the convolution between x and h2, okay? And similarly for the continuous time case as well. Okay. Now this has some system implications, right? If you do it according to the right-hand side, then from a system level, what you're doing is first passing x through a system with impulse response h1, like the figure down here, right? And passing x also through another system h2, and then adding them up to get the final output y. Okay. Now on the left-hand side, this implies that you're taking x and passing it through a system with impulse response equal to h1 plus h2, right? And this distributive property tells us that these two system architectures yield the same effective, input-output relation. Okay. Now, this is also sometimes often convenient because you can sometimes do it easier one way or the other. Okay. So here we have an example where we have an input signal x of n equal to 1/2 to the power n times the unit step function plus 2 to the power n times the unit step function, and a system with impulse response un. Now, if you want to compute the convolution between these two, you can, but it's quite tedious to do so. Right? So it's tedious to evaluate the convolution directly. But from what we just learned, we can actually, start out by decomposing xn into two signals, x1n and x2n, and I can find the convolution between x1 and h and x2 and h separately first before adding the outcome together. Okay? So this is saying that suppose we let x1n equal to 1/2 to the power n un, and x2n equal to 2 to the power n un. Okay. Then by this distributive property, we know that yn is equal to xn convolved with this hn, which is x1n plus x2n convolved with hn, and this is equal to x1n convolved with hn plus x2n convolved with hn. Okay, so we can first compute this convolution to get an output y1n and compute this to get an output y2n. All right, so this is actually obtained. This was actually obtained in example 2.3, and this was obtained in example 2.5. So if you go back and look up the result we obtained in these two examples and add them up, you find that this is the final outcome that you would get.